In this tutorial, we will discuss about serial communication with the 8051 microcontroller. Now, or we could also call it as UART, Universal Asynchronous Receiver and Transmitter. Now, before we go ahead and look into details, we'll look at why is this useful. So, this is used in, if we take a 8051 chip or a microcontroller IC, now in order to debug or at times in order to transfer code for the computer from the computer to the microcontroller, we used this UART communication. Now it comes in very handy in almost all of your projects wherein you want to debug the code, or you want to print messages and see, because since a microcontroller does not have anything pre-connected, or there's nothing which is connected, there is no display as we have on the computer. So when we write code for a microcontroller and we want to debug it, the serial terminal or the UART comes in very handy. We can print a whole lot of messages and see what is exactly happening in the code. Or otherwise, in many applications wherein we need to send data out of the microcontroller to a computer, or for instance any other microcontroller, the serial communication plays an important part. Now how does it basically work, and why is it called asynchronous? So let me just draw a simple diagram here. Now say this is a microcontroller, and for simplicity assume this as a computer. Now what happens is, the microcontroller, if we want to transmit data between these two devices, then we need a line. So say this line transmits, so this is TX for the microcontroller, and it receives on the computer side, and on the other way around there could be the computer could transmit on this line and the microcontroller will receive. Now these are the TX and the RX lines. Now asynchronous means there is no common clock between these two devices. Now why do we require a clock? Now let us take an example for that. Now say I want to transmit 1010 as binary data. Now from the microcontroller, if I make a pin high and then I make a pin low, then again I make it high and again I make it low, so this becomes R1010. On the receiver's end, on the computer's end, so we might get the same string. So now the question is, how long the microcontroller transmits this one? So is this one, or is this one, or is this one? So what is the duration of this one? So this is an essential question. So in asynchronous communication, since there is no clock which synchronizes transmit and receive, we need something else to tell both the devices what is the duration of 1 or a 0 that we transmit. So this is called the baud rate. So both the devices, the transmitter and receiver, they agree upon a common baud rate. The baud rate is a misnomer. It should be called bit rate. So we will use the baud rate itself. So both the devices agree upon a baud rate. Now say 9600 bits per second. So this means one bit is transmitted per, this is time, so this would be 1 divided by 9600. So this would be time for each bit to be transmitted if baud rate is 9600. So if both the devices agree upon a common baud rate, then we can determine the durations of ones and zeros that are transmitted. So this is kind of asynchronous communication, wherein both the devices agree upon a common data transfer rate, and that rate is called the baud rate. Now there are other types of communication wherein you have a dedicated clock which synchronizes transmission receiver, like the SPI, serial peripheral interface. So we also have this in 8051, and we will look at it on another day. There are also serial communication protocols like the USB, which are used to communicate with the computer. Now SPI is a little complicated, but the USB is much more complicated, and the best part of the UART is it is the simplest of all the serial communication protocols. Now in other controllers, if you look at AVR or PIC, the baud rate is generated by the controller itself. We need not configure any unit to generate baud rate, but whereas in 8051 timer 1 is used to generate this particular baud rate, and we'll see that and whole lot of details as to how we configure and use serial communication. Let us go ahead and look at the resistors involved in serial communication in 8051. Now whether the 8051 transmits or receives data, that data is stored in the serial buffer resistor. Now as you could see, this is a 8-bit resistor, so it means we can transmit 8 bits at a time. Now what this resistor actually does is it takes data 8 bits at a time from another resistor, and then it transmits this data serially. So the UART unit inside 8051 converts this into serial data and it transmits. So this is called the buffer resistor, which holds the data for transmission and reception. Now the next resistor is serial control resistor, or the SCON resistor. Now if you could see, again this is 8-bit resistor. Of these 8 bits, not all of these are used during normal operations. Since 8051 is a legacy controller, it had many features which are not used. So let us look at what is used and how we could use that. Now these 2 bits, so there's a table for these two. So these 2 bits, and these are 2 bits, so 4 combinations for these two. Now if SM0 and SM1, so these are mode bits for serial communication. If both are 0, it is in mode 0, and the basic source for the serial communication, or the baud rate, is 1/12 of the chord's frequency. Now this is not used. Now again, similarly, the mode 2 and mode 3 is never used, is hardly used. So one that is used widely is the mode 1. So it is a 8-bit UART, so you can transmit and receive 8 bits, and the baud rate is determined by timer 1. So this is an important point, as we mentioned earlier. So the baud rate, whatever baud rate we wish to communicate it as, 9600 or 4800 or 115K. So all these baud rates, these are determined by the timer 1. Now So these are the two bits, SM0 and SM1. Now the SM2, it is used in multiprocessor communication, wherein if you want to use more than one 8051 microcontrollers, and if you want to communicate between them, in that case this particular bit is used. So you're not going to use this. Now REN, this is called receiver enable. So for the 8051 to receive data, this bit should be 1. Now let us make as to what we should be using. So this will be 0, this will be 1, so this will be our mode 1, and then we're not using multiprocessor communication, so this would be 0. We want to enable the receiver as well, so this would be 1, and then these two bits are again not used. These two bits are used with the other modes, serial communication modes. So these, let them be 0. Now these are two important bits. Now TI and RI. So this is called the transmit interrupt, and this is called the receive interrupt. So what it does is when we place a byte in a buffer, and if we transmit the byte, as soon as the UART unit inside 8051 completes transmission of this byte, it makes the TI bit 1. Similarly, when we receive data and once we receive the complete data, the complete 8 bits in the SBUF register, the UART unit inside 8051 makes receive interrupt 1. So these are two important flags, and this we will by default will make them 0. So whenever we receive a byte or whenever we transmit a byte serially, will make the controller itself will make these bits 1. So these are basic two resistors in serial communication. So SBUF is used to store a byte which is transmitted or received, and SCON is used to configure the serial communication. Now let us go ahead and look at the baud rate in a little detail. Now the baud rate, as we know, so it is the, we can kind of call it as clock for the serial communication. So how is this derived? Now you already said that timer 1 in 8051 generates baud rate. Now let us go ahead and look how it does that. Now the 8051 basically, if we connect 11.0592 megahertz crystal, and we'll get to know why this number is so odd in just a while. So 8051 internally, this divides the crystal frequency by 12, and the UART unit, before it uses the frequency for the timer, it divides it again by 32. So what that is, so if we divide this by 12 as we have done previously, this would be 921.6 kilohertz. Now this, if I divide by 32, it would become 28,800. Now here is the thing, if this is the frequency, now this is what the timer unit uses. Now the T1, when it is configured to be used as serial communication, when we make this bit, if you make the SCON and the two bits SM0 and SM1 as 01, then the timer 1 it generates the baud rate. So if timer 1 has to generate the baud rate, it does not take the crystal frequency directly. First the controller divides it by 12, and then the UART unit divides it by 32, and then it goes to the timer. Now if you remember our discussion on timers, so if this is the frequency the timer uses, then the timer counts or increments on 1 by this frequency, 28,800. Now we can find out what the time is, but we need not do that, because what we need is a frequency itself. So 9000, say we need to configure it as 9600 bits per second. Now if we take this frequency, what you would find is this is 28,800 and what we need is 9,600. So if we divide 28,800 by 9,600, what we get is 3. So what it basically means is, if the counter counts 3, or if it does 3 ticks, then it generates a frequency of 9600 bits per second. So how does that work? Now say if the timer is 00, and since this we're using timer 1, we'll be using it in 8-bit auto reload mode. So that we'll discuss in just a while. So it is in just 8-bit mode. So if it is 00 and if it becomes 01, then this time this is 1 tick. Now 01 to 02 would be another tick, so this is second tick, and 02 to 03 would be another tick. Now if we make these 3 ticks, it generates a baud rate of 9600, because the frequency is 28,800. Now instead of starting the timer from 0, what we do is we start the timer backwards from FF. Now so we'll look at the 8-bit auto reload mode and why is it used now. If you remember the discussion on timers, so to configure the timers we have a resistor called tmod, and the last bit is gate, so this is D7. So D6 is C/T bar, then this is M1 and M0, so this is mode, and these 4 bits, these are for timer 1, and the next 4 bits are for timer 0, and for serial communication we are using timer 1, so we can make these 4 bits as 0. Now we want the timer to be in auto reload mode. So we know that if the timer makes 3 counts when it is used for UART, it generates the required baud rate. So we would hardly need anything which is more than 255. So it is used in 8-bit auto reload mode. Now if you remember, so now for this the gate would be 0, since you're using a timer this would be 0, and if you remember the mode 2 is the auto reload mode. So mode 0, it's our 13-bit reload, then mode this, if it is 01, this is 16-bit mode, and if it is 10, it is 8-bit auto reload mode. Now what happens in 8-bit auto reload mode is, like say we have 2 resistors, TH and TL, so both are 8-bit. So what happens is, whatever content we load in TH, it automatically gets loaded to TL, and when we turn on the timer it starts incrementing, and when it overflows again TH is reloaded back into TL. Now that is very helpful because we want to generate a baud rate of 9600 to transmit each and every bit. So what we do is, we know from a previous discussion that if the counter ticks 3 times, then we generate a frequency of 9600. Now instead of counting from 0 to 3, what we do is we count backwards. So say the 8-bit in hex, the highest number is FF, then the next would be FE, and this would be FT. Now we know that the counter overflows when it is FF, and if it receives 1 tick then it overflows. So this is where it overflows. Now we want 3 such ticks. So if we go backwards, this would be 1 tick, this would be 2 ticks, and this would be 3 ticks. Now if we get these 3 ticks, then the baud rate that is generated is 9600. Now what we could do is we could load this value fd in th. So this is fd, and this value will be copied in TL in auto reload mode, and what it does is it goes to fe ff and then it overflows. Now once it overflows, so we get a baud rate of 9600. Now from this discussion you should remember what should be the values of T mod. Now so the T mod should be, this should be 0x20, and we should turn this on. So before we turn on, we should load th as 0xfd. Sometimes it is written as -3, so you can do that. So let us go ahead and look at the resistors now. So we will write what the actual resistors would be. Now from the first slide, if you remember, the S-con should be phi 0. Now the T mod, we discussed it just before. So the T mod would be, so this is 2 and 0, so this is T mod would be 0x20. Now so these are the two resistors that we need to configure in order to use serial communication. Now what this does is this puts the controller in serial communication mode, and it enables the receiver, as well as it tells that the baud rate should be given by timer 1. And with T mod we configure T mod in auto reload mode, wherein we place the value which is used to generate the baud rate in th. So in th we load 0xfd or we load -3, so both will do. Now so these are the basic resistors that need to be configured. Let us go ahead and look at some of the basic code, and before we do that, what should be the algorithm to follow? So the first step is to configure timer 1. Now we just configure here in this step. So we make T mod, we set T mod here. So after we do that, then we configure the TH register, or we put the value in the TH register, whatever is required to generate the baud rate. Now next what we do is we configure the serial communication resistor or the serial resistor. So we configure S-con for the value we found out, and then we turn on the timer by TR is equal to 1. Now in order to transfer a byte, or in order to receive a byte, what we do is we do this, and then we load the SBuff resistor with the byte that we want to transfer or receive. Now say we want to transfer a byte, so we load SBuff with whatever value we want to transmit, say ASCII 0. So we load that, and then we monitor when if you remember the S-con register, there are two flags, TF and RF. So if we go back, so sorry, TI and RI. So we have two flags which tell us whether we should transmission is completed or not. So this is TI and RI. So if you want to transmit this, what we do is we load it in SBuff and we wait till TI becomes 1. So TI becomes 1 when the controller has completed transmitting the value in the SBuff. Now similarly, to receive the data, what we do is we wait till RI becomes 1. When RI becomes 1, we read the SBuff register. So we'll look at the code and we look at how we initialize and use it. Now the basic functions which we use are, this is used to initialize the serial communication, and this is used to receive a character, and this is used to transmit a character. Now with these two you can use these functions and you can build upon it. You can transmit a string, you can transmit a number, you can receive a string and receive a number, and so on and so forth. Now let us look at the init function. Now as discussed earlier, so the first step would be to initialize timer 1 in mode 2. Then we set the baud rate at 9600. This could be -3 or th1, it could be fd. This could be 0xfd as well. Now we set the scon resistor and then we turn on the timer. So this initializes the serial communication. Now to receive a character, it's pretty simple. We will wait till this becomes 1. So till the time it is 0, the while loop sits here. So it waits till Ri becomes 1. As soon as Ri becomes 1, we have our data in the serial buffer. So the data that is received is there in the serial buffer. But before we go back, we ensure that the Ri is cleared, so that next time it does not bypass this and go. So we ensure that Ri is cleared. Similarly, to transmit a byte, what we do is we take the character in the buffer and then we wait till it is transmitted. So as soon as it is transmitted, Ti becomes 1 and we exit the loop. And also here we ensure that the Ti is cleared, transmit interrupt is cleared. So this is all about serial communication. If you look at the code, these are 3 basic functions, and these will be used in other functions to transmit or receive string. So for example, UART transmit string, this function internally uses the UART transmit char function. So it will keep on transmitting characters till it finds a null character. So it is pretty simple to use, to make use of these functions and write your own function. So you can look at the code, and you could also look at an example wherein we transmit string from the 8051 to the computer. Now before you go ahead and do that, what I would like to discuss is, like, say we have 8051 and then we have a computer here. Now if you're using a computer with a legacy RS-232 protocol or a connector which is called the DB9, then so you need to convert. So since this works on CMOS, which is 0 and 5 volts, you need to convert these voltages to a level where the computer understands. And so we need a converter which is called as RS-232, so in order to use it with the computer. And if you're using a USB to serial converter, it's pretty simple. So if this is your USB to serial converter, like the CP2102 or the FT232, so what this does is, this is USB and this is connected to your computer, and this gives transmit and receive. So the transmit of this is connected to receive pin of the 8051, and receive of this is connected to transmitter of 8051, as you could imagine, and there is a common ground line in between. So these are 2 ways in which you can connect it to a computer and then transmit and receive strings. Now there are various programs that you can use. So you can use Hyperterminal, or you can use Baryterm, and whole lot of other softwares which will let you transmit and receive strings. Thank you for watching.